Today, our mathematician spotlight is Federico Ardila. He's an associate professor at San Francisco State University, and he studies the combinatorics of objects from algebra and geometry and topology and so on. So for instance, suppose you have three things, like three people, and you say, you know, I see that you're in order 1, 2, 3, but I'd really like you to stand up and change places. And so they change places, and you're like, I don't really like that either. Change places again. Well, that's like permuting three objects. Object 1, Object 2, and Object 3. And there are 6 ways to do that. You probably know that. And so you might want to know, like, okay, but I want to understand these permutations. So you might think, okay, I'm just going to make them into coordinates, 1, 2, 3, 1, 3, 2, 2, 1, 3, 3, 1, 2, and I'll plot them in 3 space. And if you do that, it turns out you get a hexagon. And so one way to understand permutations is you could just if you could connect 2 points if to get from one to the other you just switch the order of 2 objects. That's how this is done. And if you do that, you get a hexagon. So that somehow helps you to understand how combinatoric, how the permutations of 3 objects are shaped in a way that we might not have thought of before. How about if you have 4 objects? Luckily, we have 4 students sitting here. What if we want to rearrange them? We could put them in order. It's kind of hard to see these labels, but we could put them in order 1, 2, 3, 4, 1, 3, 2, 4, 2, 1, 4, 3, and so on. And if you plot those points in 4-dimensional space, and you connect them if 2 objects are switched, or 2 students are switched to get from one to the other, you get a polyhedron. What an idea. And so if you wanted to understand, like in a more tangible way, how the set of rearrangements of 4 objects is shaped, you might want to study this polyhedron, and that's the idea of what Federico Ardila is doing for these, and then for more complicated things like power series. Yeah.
Where is he from? Curious, because he's wearing like the Palestinian keffiyeh with the scarf thing.
That is a good question. I believe he is from the country of Colombia, but I forgot to look it up. Sorry. Okay, you can look it up. Yes, I was just on his website this morning to pick up this document. You look it up and then you report back. Okay, sounds good. Yes, and I met him at a conference in January. Very nice guy, doing lots of good things. All right. Oops, that was the wrong way to do that. There we go. Up, up. Okay. Colombia? Good. Whew. All right. Okay, so today we'll finish up writing things in multiple coordinate systems. So rectangular, cylindrical, spherical. You want to use whichever coordinate systems are most convenient for you. And then we'll move on to integrating over curves. So far in this class and in your life, you've integrated over like intervals, an interval of the x-axis. Maybe we want to integrate f from x equals 1 to x equals 4, something like that. Or we've integrated over regions of the xy plane. But now we will learn how to integrate over curves. So that's the idea. For instance, like suppose that it is snowy outside, which it is definitely not right now, but you want to clear a path from here to the dining hall because you want to eat, and you want to know how much snow you'll have to clear. Well, you would want to know what's the total like volume of or height maybe of snow between here, cross-sectional area of snow between here and the dining hall. And so you'd want to integrate over that curve between here and the dining hall, and this will allow us to do that. Okay, so before we do that though, let's do one final example of integrating in 3 variables. So example, set up an integral over the spherical cap, which I'll now draw. Okay, so imagine that you have an orange, and it's a very tasty orange, and you're going to cut it because you want to share it with some people. But you do a very bad job of cutting. Okay, here's the orange, and it has radius 2 inches. It is a very big orange, and it's centered at the origin, as most oranges are. And when you cut it, you don't cut right through the middle. You cut halfway between the middle and the top or whatever. So we cut not at z equals 0, but here at z equals 1. And you slice it with your knife so you get a nice planar cut. So the piece of orange that you have left is this, what's called a spherical cap. It's a piece of a sphere, but it's not an entire hemisphere. It's like less. So that's the spherical cap. And let's say it's between, let's say under, inside the sphere rho equals 2, and above the plane z equals 1. And maybe you have a function for tastiness, f of xyz equals tastiness of the point xyz, and you want to compute the total tastiness of your orange. You want to know if it's worth eating before you do so. So let's do this in 3 coordinate systems. So first rectangular, and then cylindrical, and then spherical. So rectangular coordinates. OK, we could pick any of the 3 slicing planes as our shadow plane. We could pick the xy plane or the xz plane or the zy plane. Let's pick the xy plane. So our shadow plane will be the xy plane. Maybe we'll do x on the outside, y on the inside, and then finally z. And we want to integrate f of x, y, z, the tastiness of the point x, y, z, dv. And in this case, dv is just dz, dy, dx. So here's our dv. OK, so let's set up our integration. So our shadow plane is x and y. Here's the shadow plane. So let's see what the shadow is of our spherical cap on the xy plane. So it's going to be some kind of a disk, a smaller disk, because it doesn't go all the way out to radius 2. And let's figure out what this radius is. So to figure out this radius, it's the same as the radius up there on the plane z equals 1. And we can draw in a right triangle. So the height, this small leg of the right triangle is 1, because this was the plane z equals 1. The hypotenuse is 2, because the sphere has a radius of 2. So now we can figure out the third side. You can use Pythagorean Theorem, where you can see that it's a 30, 60, 90 triangle. See, the radius is square root of 3. So this shadow plane disk down here has a radius of square root of 3. So the shadow plane is a disk of radius square root of 3, centered at the origin. OK, so let's set this up. I'll draw, again, I'll pull out this shadow plane region, shadow region. Here, x goes all the way to square root of 3, and y goes all the way to square root of 3. And if we're setting it up in this order, the dy dx order, it means we fix an x. There's my x. And we see which y's we want. So we go from y equals bottom value here up to y equals the top value here. So I think the thing to do again is to put in a little right triangle. So here, if the bottom length is x, because we're picking our favorite x value, then our radius is square root of 3 here, and we want this y value. So y is plus or minus the square root of square root of 3 squared plus minus x squared. So y is plus or minus 3 minus x squared. So at the bottom, we'd want the negative, and at the top, we'd want the positive. So our y will go from negative square root of 3 minus x squared up to positive square root of 3 minus x squared. So it might be a little strange to have this 3 here instead of something squared, but it's because our radius is square root of 3. OK, and then we want x values from all the way over here on the left all the way over to here on the right. So x should go from negative root 3 up to positive root 3. OK, boom. We've set up our shadow plane. Now the last thing to do is figure out what our z values should be. So you imagine, perhaps, that so you take your favorite point in your shadow plane. Maybe it's this point. So that corresponds to this point in the picture up here. And you take a line in the z direction. So it starts at negative infinity, goes through our other picture. That's awkward. Cuts through our shadow plane, no problem. Oh, now it pierces into our solid. And then it stays in for a while. It's now coming out the back, and now it comes out. And we want to know what's the z value when it comes in, And what's the z value when it comes out? Okay, I'll do the first one. It pops in on the plane z equals 1. So the z value where it pops in is 1. So z equals 1 because it pops in on the plane z equals 1. Okay? How about where it pops out? It pops out on the sphere. So now I have a bit of work to do. So it pops out on the sphere. So we have to write down the sphere equation in x, y, z coordinates and solve for z. So let's do that. Rho equals 2 means rho squared equals 4. And rho squared is x squared plus y squared plus z squared equals 4. So I'll solve for z. Z squared is 4 minus x squared minus y squared. So z is plus or minus the square root of 4 minus x squared minus y squared. And in my region, z is always positive, so I'll take the positive square root there. So it pops out on the sphere, where z equals the square root of 4 minus x squared minus y squared. And this is on the sphere. Yeah? Yeah. Questions, ideas? Yeah.
Trying to figure out the area, would that just be 1 dz dy dx? Or?
Yeah, so it's volume, right? Because it's three-dimensional. If you want to find the volume, you would replace this function with 1. Yeah, integrate 1 to find the volume. Yep. Yeah. And if this function was giving you tastiness at any point, you'd integrate the function of tastiness, and you get total tastiness, the orange, over the thing. Yeah. All right. So that was maybe a bit torturous because we had to, we have square roots in all of our bounds. What a mess. So it should be an indication that rectangular coordinates aren't perfectly suited to spherical things. But that's not a surprise. We hope life will be better when we switch to cylindrical coordinates. So let's try cylindrical coordinates. So we want to set this up in some order. And we want to do f. F is a function of x, y, and z. But now we're in cylindrical coordinates, so it should be a function of r, theta, and z. And then we'll integrate that dv. So in cylindrical coordinates, our Jacobian volume expansion factor is r. So we have r times dz, dr, d theta. So here is our dv. OK? And now let's set this up. So we want z equals something to something, r equals something to something, theta equals something to something. OK, so looking at this spherical cap, it looks like theta goes all the way around. So we want theta to go from 0 to 2 pi. And now r. We're setting up our shadow plane again, actually. So our shadow plane here is the r theta plane, which is the same as the xy plane. So we want all the r's and thetas to get this same yellow shaded disk region. So we want theta to go all the way around from 0 to 2 pi. And then we want r to go from here to here, or in our other picture, here to the outside of the circle. So r goes from 0 to square root of 3. Because we already figured out that the radius of our shadow is square root of 3. OK, and now the last thing to do is figure out the z's. So pick a point in our shadow plane, start the z at the end. OK, it still pops in at z equals 1. So it still pops in at z equals 1. This is on the plane z equals 1. And it pops out somewhere else. This is on the sphere. So again, we need to write our equation for the sphere and solve for z, but now in cylindrical coordinates. So we've done most of the work, actually. We already solved for z equals positive square root of 4 minus x squared minus y squared. But maybe now we can just put it in polar coordinates. Z equals square root of 4 minus r squared. So let's put that in. Z equals square root of 4 minus r squared. So that just tells you if you're at any point r comma theta, like this one, the height of the sphere above you is square root of 4 minus r squared. Kind of depends how far you are away from the origin. Seems reasonable. OK. And that was a little easier to set up, especially the outside bounds, because cylindrical coordinates are well suited to circles. Okay, let's do one more. So let's do spherical coordinates. Okay, so we want to integrate to a triple integral of f of xyz, but now it's f of rho phi theta, and then dv. Do anybody remember the volume expansion for spherical coordinates? Yeah, rho squared times sine phi. Nice. And then d rho, d phi, d theta. So now this is our dv for spherical coordinates. Nice. So we want to set it up going rho equals something to something, phi equals something to something, theta equals something to something. Okay. So let's look at our spherical cap here. So which thetas do we need in order to get the whole shape? All the way around 0 to 2 pi. Sounds good. Okay, theta goes from 0 to 2 pi. Okay, now we need to figure out which phis we need in order to get the whole shape. So phi up here along the z-axis, phi is 0. And we want to sweep phi down until we've put the whole shape in our phi range. So that would be until phi equals whatever it is along this line. Conveniently, we've already put a little triangle in here. It's a 30, 60, 90 triangle. Do you think this is the 60 angle or the 30 angle? Yeah, the 60. You know it's the 60 because it's opposite the bigger side, right? Root 3 is across from the bigger angle, 1 is across from the smaller angle. So this is 60 degrees, and if we're integrating in calculus, we need to put it in radians, so this is pi over 3. So phi should go from 0 up to 60 degrees, or pi over 3, and that'll get our whole shape. Okay, so now we have a rho phi shadow plane, which is a little bit different idea of a shadow plane. So now the idea is you pick your favorite rho comma phi, so that is a theta direction and a rho, so you're pointing in some direction like this, and then you say which, did I say theta and rho instead of theta and phi? I think I'm okay. Okay, anyway, you pick the two angles, you're pointing in some direction, and then you want your rows, which row you point into your shape and which row you pop out of your shape. So I'm going to erase this stuff for z, because we're done with the z. You pick your favorite direction to point. At some point, you pop into the solid at rho equals something, and then at some other time, you pop out of the solid. So you want rho when you pop in, and rho when you pop out. Now, rho when you pop out, that's on the sphere. So rho is just 2. So the rho when you pop out is 2. This is on the sphere. So notice that in the other cases, we had to do something to solve for where we popped out. But in spherical, the top one is easy. OK, now we also know that we pop in on the plane z equals 1. In rectangular and cylindrical coordinates, it was easy to write an equation for that, because z was one of our variables. But here, no. Yeah, but so if z equals 1, we now have to solve for that in terms of rho. So can you see a way to do that? Yeah, rho cosine phi equals z. And we know that z equals 1 when the thing pops out. So let's just solve for rho. So rho is 1 over cosine of phi. So it pops out when rho equals 1 over cosine of phi. Yeah. So that's a bit interesting that the tough one for spherical coordinates was the plane. But that's because spherical coordinates are curvy. And so if you wanted to find something flat, it's a little more difficult. So each coordinate system makes some things easier and some things harder. So you want to use the one that's best for you. Yeah. Yeah, questions or ideas? Why is it so hot? It's a good question. 81 degrees in this here. It's really hot. Why didn't I think of that when I got dressed this morning? Next time, class outside. if it's not snowing. Next time that we have a day like this, class outside. You can let me know in advance. Hey, Professor Davis, did you notice it's going to be 75 degrees and not raining next time? Could we have class outside? I would probably say yes. Okay. Okay, so the next thing we'd like to do is learn to integrate over curves. So let's talk about curves. So before class, you were probably not paying attention, but I noticed that there was a small bug that was crawling around on the blackboard. Did anybody see it? No? There was a small bug crawling around on the blackboard. Well, luckily, I was watching, and I noticed that it crawled along some path, something like this. Okay? Okay, so that's where the bug was walking. And if you just kept track of where it was at any time, you could describe the position of a bug. Here, maybe our bug is crawling on the board, but you could have a bug that flew, and then you'd have 3 coordinates for it, by r of t, which is its x-coordinate at time t, and its y-coordinate at time t. So if you're at this time t here, let's say this is maybe t equals 52, because it's 11:52, then this here is r of 52. It gives you x of 52, comma y of 52, and it tells you where that thing is. You might also want to know which way the bug is going and how fast. So this is the position. You can also get the velocity of the thing by taking the derivative. So that's just r prime of t, which is x prime of t, that's a prime, y prime of t. So this is a vector, and it's the tangent vector. So I made it look sort of crooked, so it didn't look, I didn't want to make it vertical because that would be confusing. So this is r prime of t. It's the velocity vector so vector tells you 2 things. It tells you the direction of the vector tells you which way the bug is going. And then the magnitude is the speed. It tells you how fast the bug is going. And this is just x prime of t, comma y prime of t, because if you decompose this vector into its 2 coordinates, here's y prime of t, and here's x prime of t. So how the vector of how fast it's moving is how fast it's moving in the x direction, comma, how fast it's moving in the y direction. That's a little right triangle there. You might also want to know the speed, how fast it's moving, and that's just the size, the magnitude of the velocity. So you take r prime of t, and you take its size. So that's the square root of x prime of t squared plus y prime of t squared. And then finally, you might want to know how it's accelerating. So this is just the magnitude of the velocity. And then the acceleration is how fast how the velocity is changing. So it's the second derivative. So r double prime of t, which is x double prime of t, comma y double prime of t. So the idea here is if you have the position, you differentiate term by term to get the velocity. And if you have the velocity, you can differentiate term by term to get the acceleration. OK, so given exactly where the thing is at all times, you could find out everything about how it's moving. But something that often happens in life is that you know something about how it's changing, and you want to know actually where it is at all times. So let's try that. So example. Suppose that you have a slingshot, and you're going to shoot a pebble. And you want to know how the thing is moving over time. So suppose you release a pebble from your slingshot at a 45-degree angle from the horizontal with a speed of √2 meters per second. And our question is, where is it over time? So find an equation or equations, depending on how you think about it, for its position after t seconds. T seconds after releasing the thing. So the picture is, You shoot it off at 45 degrees, you release it at 45 degrees, and at a speed of square root of 2. So that was all contrived so that its velocity vector at the beginning could be 1, 1. So we know that r prime of 0 is 1, 1. Boop. And you want to know how it's changing. And we assume that the only force acting on it is gravity, which is pulling down by a force of negative g. G is a constant in the y direction. OK, so let's do it. So negative g is an acceleration. It's measured in meters per second squared. It's approximately it's about 9.8 meters per second squared, this g. OK, so let's do this. So now we're going to start with the acceleration, which we know, and go back and get the position, which is what we want. So let's try this. So we know, so start with acceleration. So we know that r double prime of t, it's something in the x direction and something in the y direction. Let's see. Nothing is pushing on the thing in the x direction. The acceleration in the x direction is 0. And in the y direction, gravity is pulling down by negative g. So negative g. Question? No? OK. OK. So well, let's integrate this to find the velocity. So we integrate this term by term. R prime of t, the integral of 0 with respect to t is 0 plus a constant. So let's call it constant c1. The integral of negative g with respect to t is negative gt plus a constant. Let's call that constant c2. And now we plug in. So we want to know what these constants are. So plug in that we know what the velocity was at the beginning. So r prime of 0 is 1, 1. So r prime of 0 is 1, 1. So from our equation, if we plug in r prime of 0, we get c1, comma, plug in 0 for t, just get c2. So c1, comma, c2. And that equals 1, 1. So that tells you that c1 and c2 are both 1. OK, so we can triumphantly conclude that r prime of t is 1, comma, negative gt plus 1. So this tells us that that your speed in the x direction is 1, which makes sense because you release the thing with the speed of 1 in the x direction. And the speed in the y direction is 1, which makes sense because you shot it up with the direction of 1, but minus gravity pulling down. So here, its initial speed going up and gravity pulling down are kind of fighting against each other. OK, so now let's integrate and find position. So if we integrate term by term, we get r of t, integral of 1 with respect to t, is t plus some constant. Let's call it c3. Integral of negative gt with respect to t is negative half t squared plus integral of 1 with respect to t is t plus a constant, c4. Ah, g. Yes, there's a g. Here it is. Where did it go? Sorry, g. OK. Yep. OK, there it is. It was just invisible before. OK. And let's suppose we could start our particle anywhere, but for simplicity, let's start at the origin. So let's suppose that the position at 0 is 0, 0. So let's plug in r of 0 equals 0, 0. OK, if you plug in 0 for t here, you'll get c3. If you plug in 0 for t here, you'll get c4. And set that equal to 0, 0. We'll get c3 equals 0. And c4 is also 0. So this tells us we can triumphantly conclude that r of t is t, comma, negative 1/2 g t squared plus t. OK, so it tells you that your position, how much you've moved in the x direction, is just how long you've been flying, which makes sense because you've just shot it at a speed of 1. And then your position, your y is, you shot it in this speed of 1 going up, and then gravity is pulling down. All right. So this tells us our position at any time. Now it might be that you're doing this for some reason. Like, for example, you want to shoot the thing and have it land right on a student so that they will be more vigorous on a hot day. So you'd want to know, where is this thing going to hit the ground? Where are we? And when will we get there? So you could ask two questions. The first question you could ask is, when will it hit the ground? So this is like a when question about time. When will it hit the ground? Well, it hits the ground when its y-coordinate is 0. So it hits the ground when y equals 0. Let's do that. Its y-coordinate is this thing, negative 1/2 gt squared plus t equals 0. We want to solve this. Plus and t look so similar. Let's keep them different. OK, so let's solve for t. I'll factor t times negative 1/2 gt plus 1 equals 0, which tells you that t equals 0, or this whole thing equals 0. Negative 1/2 gt plus 1 equals 0. And if you solve that, you'll get t equals 2 over g. And since g is about 10, this is about 0.2 seconds. So this t equals 0 tells you that it was at the ground when it started. Not surprising, because that's where we started it. And it also tells you that, this is not a question anymore, that we hit over here at t equals 2 over g, or approximately 0.2 seconds. OK, that's a little bit useful to know that it's going to be flying for about 0.2 seconds. But we wanted to know where it lands. Where does it land? What? Yeah. Nobody knows. Yeah, so we know that, but we know it's going to be flying for 2 over g seconds. And so we just want to know the x value. And it turns out the x value is the same as t. So it hits the ground at t equals 2 over g, and it's also x is 2 over g. So if you would like to shoot a pebble at someone to make them wake up, you would want to stand approximately 2 over g, approximately 0.2 meters away, so 20 centimeters. So how far is that? This far? I'll have to stand right here. OK. Yeah, that woke you up, right? Good. OK, so that's the idea. You can use this for ballistics to model the position of a thing, find its acceleration, find its velocity, find its position. Questions or ideas? All right. Well, there's something else you might want to know. OK, the bug, it was crawling around. It got from here to here. You might want to know, how far did it go? So far, we don't have a way to do that, I don't think. Except you can maybe put a piece of string along here and then measure it. That would be OK. But we'll figure out how to use calculus to figure this out. So the next thing we'll talk about is arc length. So you might recall from life or from physics that if you want to know the distance something has traveled, it's rate times time. Sometimes it's hard to remember which one it is. Is it distance equals rate times time? Is it rate equals time times distance? Whatever. You can just figure it out by looking at the units. So rate is something like meters per second. Time is something like seconds. And if you cancel these out, meters per second times seconds, you get meters, and that all makes sense. And if you tried it in some other order, the units wouldn't work out. OK, so suppose you have some little bug, and it's going along, and you want to know, how far did it go? Well, you could ask it at each point, how fast are you going? Each second, you could say, how fast are you going? The next second, you could say, how fast are you going? And then you could multiply rate times time, figure out how far it went in each second, and then add those up and get how far it went in the whole time. So the arc length, the way we do it is we add up the speed, so the magnitude of the velocity. So this is the speed. And then we multiply by dt. So this is a time interval. A little tiny time interval dt, just from one moment to the next. And when you add this up, it's rate times time. So this whole thing is a little distance traveled. Distance traveled in a tiny little time interval. So we would add up all the little distances traveled in these tiny little time intervals. So maybe from t equals a here to t equals b there. So we would add them up from t equals a to t equals b, and that would give us the entire length of this curve. So we're adding up the little tiny distances to get the whole distance that we traveled. That's the idea. Okay, so that's how you find the length of a curve. You just find the magnitude of the velocity and integrate it dt. This is what I claim, but you should be skeptical. You should think, I want to make sure it works. Let's try it out on something we know. So let's try out on the length of a circle of radius r. Okay, the length of a circle of radius r, we expect, what would you expect? Yeah, 2 pi r. The length of a circle is also known as the circumference, so you expect to get 2 pi r. And here I'm using big R so that we don't get confused with the little vector r that tells us where we are. Okay, so here's our circle of radius r. We need to give our position. So r of t is, well, we usually do radius times cosine t, comma radius times sine of t. So to go around a circle, a unit circle, you would do cosine of t, sine of t. And since it's r times as big, we'll do r cos t, r sine t. Okay, so to find the arc length, we'll do from t equals 0 to t equals 2 pi of the magnitude of r prime of t times dt. So we better find the magnitude of r prime of t. So we, I guess, should compute r prime of t. So the derivative of r cos t with respect to t is negative r sine t. And the derivative of r sine t with respect to t is r cos t. Okay? So we would like to find the magnitude of that. Yeah, can you figure out the magnitude of this? Yeah? Yeah, it's just r. So one way of thinking about this is if this vector, we call it x comma y. So if we call this point here x comma y, then r cos t is x and r sine t is y. And x comma y is this vector. Then the velocity vector, check that out. It's negative y comma x. So it's actually exactly the same magnitude as a vector as our distance from the origin, which we know is r. Or you can use the Pythagorean Theorem. So this is just r dt. And so if we integrate r dt, we get rt from t equals 0 to t equals 2 pi. So we get 2 pi r, which is what we wanted. So it works. So you should have a bit of confidence that this might be a good way to calculate length, because at least it works for the circle. Yeah? Yeah, if we didn't use the magnitude of this vector, it would just be our speed, which would have the direction included. Okay, so for one thing, if we didn't have the absolute value, this would be a vector. So you'd be integrating a vector dt. So it would be hard to know what that means. I guess you would be, integrating r cos t, comma r sine t dt integral. And so it would be hard to know what that means, right? But maybe it would mean integrate term by term, integrate this and then integrate that. And that would tell you that exactly. You went nowhere in the x direction and you went nowhere in the y direction. They would both come out to 0. So it would be like a net calculation. We have to be sure to set this up carefully, what it means. Yeah, so we use the speed so that you get credit for going around even if you end up back where you started. Yeah. Let's take actually a look at this. So the r of t is x comma y. So this vector from the origin is x comma y. And this tells you that your velocity vector at any point is negative y comma x. So if here's x and here's y, we do negative y comma x. Tells us that our velocity vector is going that way. Does it make sense that your velocity vector would be going that way? Yeah, you can imagine that the circle is like you have a ball in a sock and you're spinning it around your head, and its velocity is whichever way it would go if you let go of it. And you can imagine if you let go of it, it would go spinning off that way. So that's the idea. It's perpendicular to the direction of motion. While we're at it, let's compute acceleration. Oops, that was supposed to be an r prime of t. Let's compute the acceleration, r double prime of t. Can you differentiate this thing? Let's see. Negative r cos t, negative r sine t. And I can recognize that this, well, r cos t is just my x. So this is negative x. And negative r sine t, that's just my y, negative y. So it tells you that the acceleration actually points in the opposite direction. Here's r prime of t. And the idea is that acceleration is how velocity is changing. So if you were to let your sock go at any point, the ball would go flying off this way. And the reason it doesn't is because something's pulling it in. So that means the acceleration is what's pulling it in towards the center of the circle. So that's the acceleration is radial, and the velocity here is tangential. Yeah. Okay. Okay, so what we did here is we computed the length of a circle or its circumference, which is something you already knew. Let's compute something that you didn't know before you came in here today. Okay. So suppose that there is a bug and it's lazily just spinning or going around in a circle, going towards the ceiling fan where things are light and warm and wonderful. Doesn't it sound nice? Okay, so we have this bug and it's going around in a circle. I'm going to draw this from the top so that my in front of everything is on the right side. Okay, so this guy, the bug starts here at t equals 0. It goes around in circles in a spiral helix shape until t equals 2 pi. So suppose a fly's position is given by r of t, which is cos 3t sine 3t t in feet, and t is in minutes. So it's just going around and around. So cos 3t sine 3t, that's very much like cos t sine t. It's just like a unit circle going around. So it tells you that the shadow of the bug's movement, the fly's movement, is just a unit circle. But the 3t tells you that it's going around 3 times as fast as normal. So its shadow here is going around 3 times as fast as you might expect. And then the t means that its height is however much time it's been going. So it goes up as time passes. So let's find the distance flown from t equals 0 to 2 pi. So the length of the thing that I've drawn there. Let's do it. So we know already, we'll need the speed, so we'll need the magnitude of the velocity vector. So we better compute the velocity vector first. So r prime of t. Okay, derivative of cosine of 3t is negative 3 sine 3t. Derivative of sine 3t is 3 cos 3t. Derivative of t is 1. So let's find the magnitude of this. So the magnitude of r prime of t, let's see. If I add these two, if I square these guys and add them up, I'll get 9 sine squared of 3t plus 9 cos squared of 3t. So I'll just get 9. So it's the square root of 9 plus 1, like 1 squared here. So it's the square root of 10. So the 9 here comes from, so if this was just square root of 9, the speed would be 3. And that's because we're going around three times as fast as usual. And the extra 1 here is because we're also going up. So that's where the square root of 10 comes from. And this tells you that the thing is traveling at a constant speed. So by the way, this is a constant speed. OK, so let's integrate to find the length. OK, so the length is the integral from t equals 0 down at the bottom to t equals 2 pi up at the top of the magnitude of r prime of t dt. And again, this part is the rate, and this part is the little time increment. So rate times time gives us the whole distance. So let's plug in what we know. So we're going from t equals 0 to t equals 2 pi. The magnitude of our velocity vector, that's just our speed, is square root of 10, constant speed, times dt. So when we integrate this, we get square root of 10 t from t equals 0 to t equals 2 pi. This just says you're going square root of 10. So the distance you go is just square root of 10 times however long you're going for. So we get root 10 times 2 pi, where this part is the rate, and then this part now is the total time. And so that whole thing is the distance. Cool. Yeah. So if this were just going around the unit circle 3 times, we would know that the circumference of the unit circle is 2 pi. So we go around 3 times, we get 3 times 2 pi. 3 times 2 pi would be square root of 9 times 2 pi. Square root of 10 is a little bit bigger, and that's because we don't just go around in a circle 3 times, we also go up. Yeah. OK. OK, so it's very useful to find the length of things. We didn't know how to find the length of a helix before today. And what we'll be doing with this is integrating functions over curves. So you can imagine that you are, let's say, you're shoveling a path to the dining hall. So here's you. We're in room, whatever room we're in, 104. And here's the dining hall, Sharples. And there's so much snow everywhere on the ground. It's piled up. Who knows what it looks like. You can imagine it's like the surface of the snow is some bumpy thing. But we are going to shovel a path to the dining hall that's 1 foot wide. And we want to know what's the total volume of snow that we have to shovel. So that would be the area of this thing. So you have your circuitous path that you take when you're going to the dining hall. And at each path, there's a height of snow that you had to shovel there. So this is like some function. OK? And you want to know what's the total amount of snow. So if f of xy is the height of the snow at the point x, y, and this is your curve C, the path you take to the dining hall, the total amount of snow, so the cross-sectional area, if you will, of, so side area of the snow, is the integral over this curve C of f of xy times, well, times like a little dx type thing. You're basically like f of xy dx, but it's not exactly dx. Dx would mean if you're just going along the x-axis. here you're not going along the x-axis, you're going along this curve. So it's like dx, but it's along the curve, and so we call it ds, to say that it's like arc length along our curve C. So if you wanted to know the total amount of snow, you would integrate f of xy along the curve ds. And that's what we'll do. All right. All right, thanks everyone.